Today we are going to find out the potential difference in potential due to a point charge. Here plus q is the point charge and it is kept at a distance O. Because of this, electric field is lying in the area. Q naught is the test charge that is being moved within this electric field of plus q charge. Let it is being taken from A to B. In between, we have taken a small distance, that is between C and D, as a very small distance denoted by dr. Now, before taking up the topic, we have to consider few things within here. Here the test charge Q naught is brought from A to B, that is against repulsive force in the electric field of source charge plus Q. This plus Q charge is going to offer the repulsive force for incoming Q naught charge. Now, the following points are to be considered. The first one is this Q naught charge is so chosen that it is small, very small, so that it is not going to interfere the field of plus Q charge. Otherwise, if the value is more, it will have its own electric field and then two electric fields will interfere. So it is so small that it is not having its own electric field to be interfere with the Q. So this is our first consideration. The second one is this: the force on Q naught is sufficient to encounter repulsive force. Since it is experiencing the repulsive force and we have to make it move, so we have to apply the external force. So that external force should be so small that it is not going to interfere the force produced because of this plus Q charge. So the force on Q naught is only that much that it will encounter the repulsive, it will balance the repulsive force of this plus Q charge. Since it is a conservative field means the work done, if the work is being done on any of the path, the nature of path is not important, only the initial and the final points are important. So since it is a conservative field, so along any path maybe anyone, the work done will remain the same for the initial and the final points. Now, let at any instant charge Q naught is at C. Now we can see the distances also. We have to take the charge from Q naught charge from A to B. So we will find the distance from the point O where plus Q charge is placed. That is at distance RB, and at the A is at a distance RA, and CD is any point we have considered. So C is at a distance R from point O. Now, at any instant charge, Q is at C, Q naught is at C, then force experienced by it due to electric field of plus Q charge is given by F force is equal to, since electric field is force per unit charge, from that relation we found that force is equal to Q naught E. Now we'll put the value of electric field, that is 1 by electric field is because of plus Q charge, so its electric field will be given by 1 by 4 pi epsilon naught Q by R square. So let us mark it as equation number 1. Further, Q naught is moved to distance small dr from point C to D. Now, to make it move from point C to D, we are applying the external force, and the external force will be in the opposite direction as the force given by plus Q charge. So, the dr is the distance traveled within this point C to D. The work done will be equal to, it is a small work done for the small distance moved, it will be given by force into distance, and in case it is opposite to this force produced by plus Q charge, so that is why the minus sign is here. So F exterior into the distance traveled is also equal to the force produced by the plus Q charge within this distance. Now when we will put the value of F from equation number 1 here, we get the small work done is equal to minus 1 upon 4 pi epsilon naught Q naught over R square d. Now, if we want to get the total work done in moving the charge from q naught charge from A to B. We will integrate the equation. Now, total work done in moving q naught from A to B is given by putting the limits, because it is integrated with respect to the distance. So we'll put the limits of distance only, RA RB minus 1 4 pi epsilon naught q naught r square dr. So on integrating, we get the work done is equal to minus 4 pi epsilon naught q naught now on putting the limits, we get now we see that this is the work done in moving the charge from point A to B. So we denote it by the work done A to B, and this is the equation for the same. On integrating, we have got this work done is equal to 1 by 4 pi epsilon naught q naught 1 by r and the limits. On putting the limits, we will get this equation. Since the work is being done from moving the point from A to B, we have denoted this work done with the this suffix AB. But potential difference between A and B, according to the definition of potential difference, is equal to work done per unit charge. So VB minus VA will be given by this relation. Now putting the value of work done from A to B, from above equation we have VB minus VA is equal to 1 4 pi epsilon naught Q 1 upon RB minus 1 upon RA. So this is the equation that we have found out for the potential difference. Again, rewriting the equation for the potential difference, we are having VB minus VA is equal to Q by 4 pi epsilon naught, and the limits for this have been put. Now, if A is at infinity, then this distance RA will be replaced by infinite, and that will come out 1 upon infinite will become 0. So VB will be equal to 4 pi epsilon naught over R. Since VA potential will be 0 for infinite distance, so we get the potential at B is equal to Q 4 pi epsilon naught by 1 upon RB. Or in general, this potential is 1 by 4 pi epsilon naught Q by R. So this is the relation for the potential. We have found out the potential and potential difference due to a point charge in my previous lecture. The link is shared here. Now we are going to do a very important conclusion out of that. That is, the work done in moving any unit charge along a closed path that is lying in the electrostatic field is equal to 0. And if this is the condition, it confirms that electrostatic forces are conservative in nature, as it is not depending upon the nature of path, it is depending upon the initial and the final points. And for any closed path, if the work done is coming out 0, it means it is conservative in nature, and that is what electrostatic forces are. To prove it, we have considered the plus Q charge at position O, and let any test charge Q naught is being taken from A to B and then B to A. So this is completing one closed path, and the nature of path may not be a straight line, it may be a curved or any sort of line it may be. along which it is going to move. Now, the work done in moving the test charge Q naught from point A to B. So this expression I have mentioned, I have already taken it out. I have already proved this thing. So work done along path L is given by L1 is given by Q by 4 pi epsilon naught from point A to B, and the limits are on putting the limits 1 upon RB minus 1 by RA. Similarly, the work done in moving the test charge from point B to A is given by this expression. Now, adding these two equations, we will get the total work done along the closed path, work done from A to B and then work done from B to A. So, the work done in the closed path comes out to be adding equation number 1 and 2. And this comes out to be 0. Therefore, the total closed path work done is 0. It confirms electrostatic forces are conservative in nature. So this is about proving the nature of the electrostatic forces as conservative.